Welcome back, students. This way, we're still under differentiation, right? We are going to talk about the related rates. Now, what is related rate? Related rate is actually the differentiation of something related to time. So we have differentiate of something with the respect of time. So we call it related rate. Now, our objective for this lesson is to find the related rate and use the related rates to solve real-life problem. Okay, so let's start with the example, right? Because actually the concept is differentiation. We are going to apply this differentiation in a real-life problem. So now the example goes like this. A pebble is dropped in a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripples is increasing at the rate of 1 foot per second. Now, so you can imagine, right? So this is the ripples. So the ripples always go in circle. Okay. Now, as the ripples increasing, so the outer, this outer ripples increase at the rate of 1 foot per second. Okay, so the English people always use foot, right? So 1 foot per second. So we have 1 foot per second. Now, when the radius is 4 feet, at what rate is the total area of the disturbed water changing? Now, so we can imagine when the radius is 4 feet now. This is 4 feet. Okay, so when this is 4 feet, now we know that this river, all right, is increasing. So the area is increasing as well. So we wanted to know at what rate, right, the area was changing or is changing. Okay, now, so first, since this is related to area, so we need to have the area formula. So the area formula is pi r square for a circle. Okay, so now according to these questions, so this value is given 1 foot per second. Now when we look at the unit 1 foot, so this one is actually the radius. Okay, right, the difference of the radius, and this is the difference of time. Therefore, right, we can have the difference of the radius, which is over the difference of time is actually 1 foot per second. So now what do we want? We want to find out what rate the area is changing. So we want to find out what is the difference of area with respect to difference of time. Okay, so when we have the rate, remember, right, when we have the related rate, it's supposed to have differentiate something with respect to the t. All right, so in this case, it's the differentiation, the difference of area with respect to the time. So this is what we want. Okay, now if this is what we want, dA dt, and we have dr dt, and also we know the formula of area. So how can we actually find dA dt, right? So now actually from here, so you can see here when we multiply dA dr, we can eliminate the r, right? So when we eliminate the dr, so we have dA dt. So in this case, first we need to find the dA dr. So we differentiate the a with respect to r. And from here we have 2 pi r. So substitute 2 pi r inside here. Now the dA dt will be 1 times, right, dRdt is 1, multiply dA dr is 2 pi r. Now, according to the question, right, it also mentioned that the radius is 4 feet. So if the radius is 4 feet, so now we know the r is 4, and we are going to substitute here, right? So substitute the r is 4, therefore we have 8 pi. All right, so what is the unit? Since this is area over time, so we have feet square per second. So this is the rate where the area of the river increasing. So every second, the area of the river increased by 8 pi feet. Okay, so this is one of the example. All right, so you can refer this former solution, right on the slide. Okay, so 8 pi square feet per second. So the guidelines for solving related rate problems. First, we identify all given quantities and the quantities to be determined. So make a sketch and label the quantities. So you can sketch a diagram, right? So that you can understand the problem clearly. Write an equation involving the variables whose rate of change either are given or are to be determined. All right, so you can actually write the equation, right? The equation for the rate given, right, which are given or to be determined. So there are two here. So after that, all right, we are using the change rule, all right, we differentiate, right, the equations. And after that, we actually substitute into all the known value, all right, for the variable, and then we can actually solve the required rate of change. Now, the table below here lists example of mathematical models involving rate of change. Now, for example, the velocity of a car after traveling for 1 hour is 50 miles per hour. So, right, the variable is the x, is the distance traveled. And the differentiation, the rate is dx dt, which is 50 miles per hour. All right, so when the t is 1, right, 1 hour, it's the t. Now the second one, water is being pumped into a swimming pool at a rate of 10 cubic meters per hour. Okay, so what is the variable? So since water is being pumped into swimming pool, so the volume is the variable. And what is the rate? The rate is actually the difference of volume over the difference of time, right, dv dt. All right, so it is 10 cubic meter, so 10 m to the power of 3 per hour. Okay, the third one. A gear is revolving at a rate of 25 revolutions per minute. So 1 revolution is equals to 2 pi radian. Okay, so you can imagine, right, the gear is turning 25 revolutions in a minute. Okay, so in this case, what is the variable? The variable, we can use the angle of revolution. So the rate will be d theta dt, right, the difference of the angle over the difference of time, which is 25 revolution, multiply 1 round is 2 pi radian angle. So you can imagine, right, it's turning. Okay, so when turning 1 full circle, we call that 1 revolution. So it is 25 revolutions, and each revolution is 2 pi, right? 1 circle, 2 pi radian. So we have 25 times 2 pi radian per minute. Now, example number 4 here. A population of bacteria is increasing at a rate of 2,000 per hour. So what is the variable? The variable is the number in population, the number of bacteria actually. So what is the rate? The rate is dx over dt, the difference of number of bacteria over the difference of time, which is 2,000 bacteria per hour. Okay, now we have another example here, right, about the rate. Okay, so water is poured into an inverted conical container at the rate of 6 cm cube per second. So the container has a height of 15 cm and a base radius of 9 cm. So what is the rate of water level rising when the water level is 6 cm? So you need to give your answer in time. Now first, we are going to label, draw the container, right? So to understand the question better. Now, this inverted cone, right, is the container. The base radius is 9 cm. So we have 9 cm here, the base radius. And the height is 15 cm. So we have the height is 15 cm. Okay, so when the water is poured into the container at the rate of 6 cm cube per second. Okay, so what is this? So this is volume, right? 6 cm cube is a volume, and the second is actually the time. Therefore, we know that this is actually dV dt. The difference of volume over the difference of time. So this is the rate, 6 cm cube per second. So when this amount of water is poured into the container every second 6 cm cube, so we can imagine that the water level is actually rising. Okay, and all right, in the beginning, maybe the water level is rising faster. Why? Because the space here is small. So has the water level rising, all right, the space of the cone become bigger, and then the water level rising at a lower speed. Now, we want to know what is the rate of water level rising. So again, the rate here refer to dt. All right, water level is dh. So we want to find this, the difference of height over the difference of time. So we have this one, h, right? This is the height. And actually, this is the radius of the water level. Okay. Now, after we now know that this is the rate given, this is the rate that we are going to find. So what is the equation that relate these two? All right, the relation relate the V and the H, right, will be the equation of the cone. All right, so we have, this is the equation. So the equation is 1 over 3 pi r square h, so the volume of the cone. Now from here, actually we can see, right, this equation consists of two variables. All right, the r, which is the radius, and the h, which is the height. Now when we differentiate, right, has the r changed, the h changed as well. All right, so we cannot just differentiate the h only without affecting the r, because when the h is changing, okay, when the h is changing, the r also changing. All right, so when the water level increase, the r, the radius of the water level become bigger. All right, so we need to solve this part first. We need to change this the variable r and h into one variable only, which is variable h, right? We are going to differentiate later. So in this case, we are going to use the triangle here. Now, from these two triangles, this is the cross section of the cone, 9 cm, and this is the height of the cone, 15 cm. Now, as we compare to the water level, all right, the water level is here. This is the R of the water level, which is always changing. And this is the H, which is the height of the water level. Now, we can see here they are actually a similar triangle. So we can actually write the ratio. Now, the R over H, right, this R over H, the ratio is actually equivalent to 9 over 15. Okay, so we have R over H here, okay, equals to 9 over 15. And from here, we can actually replace the R with H. So we bring the H over right-hand side, and we have the R equals to 3 over 5H. Now, substitute this one into the equation here. The volume will be 1 over 3 pi 3 over 5h square h. Okay, and simplify this. Now we have, this is 3 square, which gives us 9. And this is 25, multiply 3, we have 75, but I'm going to write 3 times 25 here. Okay, so simplify this, we have 3 here. Okay, so now after that, we have h square, multiply h, we have h cubed, and we have a pi. So we're going to write pi h cubed here. So this is the volume, all right, the equation of volume in terms of h only. Now, after that, we are going to relate this one, the equation v, in terms of h, all right, with the dv dt, this one, dv dt, and dh dt. So we know that actually dh dt, this dh dt is what we want to find, and we have dv dt. Now, so what do we need? Okay, what do we need here? We need dh, so we need to have a dh here. And dt is, this dt is what we need. We do not want the dv, so we are going to divide it by dv. So we are going to find this dh dv, which is the inverted of dv dh. So we can actually differentiate from here, dv dh, which give us 3 bring down, multiply 3 is 9, and over 25 pi h squared. Now also the question mentioned that, right, the water level is 6 cm. So now we know the h is 6 cm, and we are going to substitute this h equals to 6 cm here. All right, so we have dv dt equivalent to 9 over 25 pi 6 squared. Okay, now, so, okay, this is the h actually. So after that, we are going to invert this, substitute here. The dv dt is from here 6 cm cubed, and then we can actually find the dh dt. Okay, so therefore we can actually see that now the dh dt is equivalent to 6, all right, This is dv dt, 6. All right, substitute here. And the dhdv, which is the inverted of this, all right, 25 on top, 9 pi h square, all right, denominator, and the h is actually 6 cm. All right, substitute 6 cm here. Okay, and solve it, we have this rate, right? The height of the water level is increasing at the rate of 25 over 54 pi cm per second. All right, so this quantity, right, since this is height, so we know, right, it should be cm, and dt should be the second. We follow the given one. All right, so that's all about the related rate. And so make sure, right, to solve these questions, right, as a summary, first, you can actually draw the diagram, all right, to understand the problem better. Write down the given rate and the rate that we need to find. After that, identify the equation that relate these two given, the given one and the one that we want to find, right? Write an equation to relate these two. And finally, right, use the chain rule, okay, to find out the differentiation. All right, so differentiate, and after that, substitute all the value inside so that we can get the rate of change.